Hey, welcome everyone. My name is Jason Weaver. I'm a professor at Brigham University in Utah, United States. And I'd like to share a little bit of research that one of my grad students did, John Lynn. It was published in Materials Journal not too long ago. So we'll be talking today about looking at the interfacial strength between additive manufacturing material through powder bed fusion and the substrate that it's printed on. So by means of introduction, the scenario that we're looking at is the capability of printing new material onto an existing part. And some of the times when this might be really useful, one is when we have a part that has been manufactured in some other way, maybe it's wrought or formed or machined, and we want to add additional material to it. Like you can see in the turbine at the top of the page, it might be convenient to make the core through conventional machining, but then additively create the fins or the complex geometry. Another area where this can be really useful for us is when we are reworking or repairing something. You can see along the bottom, this same turbine, you can have one of the fins be damaged, and instead of having to scrap it and manufacture a new turbine, you can go in and additively, you can add material there and repair it and get back to your original geometry. There are a few different ways of additive manufacturing of metals. Two of the main ones here are DED, directed energy deposition, and powder bed fusion. It comes under a lot of different names, SLM, DMLS, laser fusing. There's a lot of different variations. For the scenario that I was talking about adding additional material to an existing part, we typically use directed energy deposition. You can see in the top picture, this is where we're spraying a powdered metal typically, and then at the same time creating a melt pool by shining the laser on the material as it's fusing to the substrate, the existing part. This is really flexible. You can put it on a robot arm and get a lot of different degrees of freedom, but there are some downsides. It is fairly rough. There's not a lot of accuracy or the ability for fine detail in this process. And it's not as well known in industry. A lot fewer people have this DED type of equipment compared to the alternative, which is the powder bed fusion. This is becoming very standardized in industry. There are a lot of locations where you can do this process. It has much better resolution. You can get really fine details. It's fully dense metal. But we are limited for this scenario because we're using a bed of powder. So we're typically starting at the ground level with no existing material and building on a metal print bed surrounded by powder. And so even if we were building on an existing part, that part would have to have a very level flat surface, and then we're building up in the Z direction from that. So the question for our research was, can we use this powder bed fusion process that's a little bit more well-known and has the better accuracy and resolution? Can we use that in the scenario where we are building on existing parts? And the specific question that we were looking at is, what is the material properties at that interface where we have the existing wrought print bed or existing part and we're printing on top of it? What's happening at the boundary? So for our method, we took stainless steel 316L in a wrought block and put it inside a powder bed machine and an EOS. And from there, we built additional material also out of the same stainless steel 316L on top of it. So in the picture on the left, you can see one block is completely additively manufactured. And then the one on the right is half the original wrought material and then half the powder bed fusion material. You can see that there's a slight difference in the surface finish, but it makes a very good solid product. After we had created these blocks, we machined them down into conventional samples. So we were able to make tensile samples and torsion specimens. And for each one of these, you can see that half of the specimen is the wrought material and half of it is the additive manufactured powder bed fusion material. We also created samples for microscopy. Again, we had a small rectangular sample that has half of the wrought and half of the powder bed fusion, and then polished them so we could look at it under a microscope and also look at it with electron backscatter diffusion. Here's some of the equipment that we used. We did our torsion and tensile testing in an Instrom 1381 machine. We did microscopy observations at 32 and 63 magnification, and then we did some EBSD grain maps. So what did we find? Well, here's our results for tensile testing. So we had several specimens, several samples of each variety. These are the average results. But you can see the orange is the powder bed fusion, the additive manufactured material. The blue is the conventional wrought material. And then the black curve is our hybrid half wrought, half PBF material. And you can see we measured the yield strength and the ultimate tensile strength for each of these three varieties. Took a look at the mean and the standard deviation, all the normal measurements there. Same thing with our torsion testing. We can see the three different curves. We've got our tensile strength and the shear modulus that we recorded. Here is an example of our microscopy. You can see at 63 magnification that there's a pretty decent boundary between our two types of material. We didn't find significant voiding or anything that would cause us concern there. And then finally, here are the grain maps. On the left, we have our wrought stainless steel, and on the right, our powder bed fusion stainless steel. You can see that the grain size of the powder bed fusion is a little bit smaller, a little finer. So instead of 60 microns, we're down to 48 microns. So what does all that mean? Well, as we're comparing our original wrought material with our powder bed fusion material, we found that the PBF specimens had a higher yield strength, 70%, so quite significant, a higher ultimate strength, and a higher torsional strength, so higher strength overall. We did find that it had lower ductility, so it was more brittle. It had less elongation as it was being pulled. And this falls right in line with what we'd expect with the Hall-Petch relationship, which in general says that yield strength will increase in a material as we get smaller grain size, and that correspondingly ductility will decrease with the smaller grain size because we don't have as much slip between the grain boundaries. So this matches exactly what we found, that the PBF grains were smaller than the wrought grains, and it showed that same increase in strength and decrease in ductility. For our hybrid specimens, which is really what we were concerned at, we wanted to find out if we were at least as good as the original material. We didn't want our additive portion of the part to shear off from the original substrate and have that failure at the interface. But we found that we did not have any failures at the interface. Almost all of the failures and deformation occurred within the wrought portion of the part. So because we saw that the wrought material was a lower strength than the PBF material, almost all the deformation was limited to that side of each specimen. And as we saw in the charts, the stress and strain behavior of these hybrid specimens was very similar to what we found in the wrought specimens. And that makes sense if most of the deformation is occurring in the wrought area, not at the interface or the powder bed fusion path. We did see less elongation in these samples, and that makes sense if this elongation is still happening in the wrought section, but because the wrought material is only half of each sample, we have a lot less material to play with and to elongate before failure. And then as we saw before in the microscopy, we didn't find any significant voids in the interface, which is also very good for the application. So in conclusion, we found that the strength at the interface between the additive manufactured powder bed fusion material and our wrought substrate material, that strength exceeded the original strength of the wrought material. And we also saw that the additive material itself was also a higher strength than the wrought material, but lower ductility. We were able to confirm that the Hall-Petch relationship does ring true with our observations. It does a good job of explaining why we saw what we saw. And overall, we found that this idea of adding additional material additively to existing parts, where part of it is wrought and part of it is powder bed fusion, that is a feasible idea. From a strength perspective, it does work. It's a promising option for repair and these other design processes where we may want the advantages of PBF over DED or other alternatives. And that is all we have for you today. So thank you very much. It was a pleasure to be able to present to you. And I'd love to discuss it with you some more.